Hello. Today we will start with the second chapter, current electricity. So what we have seen in the first chapter? We have seen about the charges which are at rest. So charge which is at rest, will it produces electricity? Isn't it? Will it produce electricity? A charge which is at rest? No. So a charge which is in motion, when the charges are made to flow, that produces electricity. That we call it as the current. So in this chapter, current electricity, we are going to see about the charges which are in motion. So we are going to make the charges to move from one end to another end, and we are going to see what are the consequences of this. Now, how I can make a charge to move? How I can make a charge to flow in a specified direction? How I can make? See here, for example, this is your, it's a lake. Here water is there. I want to make the water to flow. What I can do? So here the base of the river is exactly horizontal. Will the water flow from this end to this end if the base is exactly horizontal? So just imagine this is a river. You imagine any river. It may be Ganga, Kaveri, Krishna, whatever it may be. If the base is exactly horizontal base, will the water flow? No, definitely not. Now what I am going to do? I am going to lift one end of the river. So what happens? So this end I am going to lift it up. So here its height increases. At this end the height is more when compared to this end. So what happens to the potential here? What happened to the pressure here? At this end where the height is more, the pressure is more than this end. So when there is a pressure difference between these two ends, the water will flow from end where the pressure is more to end where the pressure is less. Now the same technique we are going to use in the electricity. This way I can make the charges to flow from one end to another end. So imagine this is a metal, this is a conductor. Here we know all metals are very good conductors. What that means? I can make the charges to flow from one end to another end. So this is a wire. In this wire I can make the charges to flow. How I can make the charges to flow from this end to this end? What I have to do, I have to make or I have to create a potential difference between this end to this end. There should be some potential difference from this end to this end. If these two ends are at the same potential, the charges will not flow from this end to this end. So what I have to do? I have to make this end or either of this end to be at a greater potential than the other end. So if I do like this, the charges will be flowing from an end where its potential is high to an end where its potential is less. So this is the way I can make the charges to flow. So in this lesson we are going to see about the charges which are in motion. Now we know that all metals are very good conductors, isn't it? All metals are very good conductors. That means a metal will allow the charges to flow through it. What it will do? It will allow the charges to flow through this. Now in nature we can see, in our everyday life we can see so many examples where the charges are flowing. For example, when there is a lightning, what is happening during lightning? The charges are flowing from the cloud to the earth through the atmosphere. So when there is a lightning, what is happening? Here there is a cloud, the lightning effect. This is your earth. The charges are flowing from the cloud to the earth through the atmosphere. Here the charges which are flowing, this constitutes the current, but they are not in a steady manner. The charges which are flowing are not steady. Can you say some examples where the charges are flowing in a steady manner? In our everyday life we can say so many examples where the charges are flowing in a steady manner. Can you say any one example? So imagine this is a torch light. What happens when you switch on the torch? You can see the light coming out of it. Here, this in the example, in the torch light, the charges are flowing in a steady manner. And then so many examples. A clock, you take a clock. So the clock is driven by a cell which provides the energy for the charges to flow. Here also the charges are flowing in a steady manner. So the charges, so this example for lightning, here the charges are not flowing in a steady manner. Here the charges are flowing in a steady manner. That is in the case of a torch light or a clock which is driven by a cell. Now we will see how the charges are flowing in a metal. We know all metals are very good conductors. What will happen? What makes the electron to move. Now you take a conductor, any metal, it is an uncharged metallic conductor. Just imagine this is a uncharged metallic conductor. Clear? Now in this uncharged metallic conductor, some electrons, not all the electrons, few electrons will be loosely bound to the nucleus. Some electrons, imagine this is an atom, this is a nucleus, electrons will be revolving around the nucleus in a specified orbit. Now, few electrons will not be tightly bound to the nucleus. These electrons which are not tightly bound to the nucleus, the thermodynamic internal energy of this material is sufficient to pull out the electron from the atom. So, here these electrons which are at the outermost orbit are not closely bound to the nucleus. The thermodynamic internal energy of the material is sufficient to knock out this electron from an individual atom. Now, this will become a positive ion, and these electrons which are taken out from the atom, they will be moving inside the conductor in a random direction. They will not move in a specified direction, a definite direction. How they will move? They will be moving inside the material or inside the conductor in a random manner. Clear? Now, these electrons, which we call it as the free electrons. So, the electrons are moving like this. So, when they move inside the conductor in a random manner, they will collide with the positive ions. What they will do? They will collide with the positive ions. Clear? For example, this is the electron. It is going to collide with a positive ion. It gains some speed. Clear? Because it is not bound to the nucleus. It is totally free out of the atom. So, it will be moving in a random manner. It goes and collides the positive ion. With some speed, it will be going and colliding, isn't it? So, with what speed it is going and colliding the positive ion, with the same speed, it will be returning back. Clear? So, it just comes out with the same speed. With what speed it is going to collide with the same speed, it will be coming back. That is, the speed before collision will be equal to speed after collision. Clear? With what speed the electron is going to collide? With the same speed, it will be emerging out. Now, if you see the speed, magnitude of the speed will be the same, but the electron which is emerging out after collision will be moving in a random manner. It won't move in a steady manner. So, what it will do? It will move in a random manner. So, you take any point. At any point in this conductor, since these electrons after collision, since they are moving in a random manner, if you take at any point, the number of electrons which are crossing this point with the same speed will be the same, or it will be equal to the number of electrons traveling in the opposite direction. So, you take this point. In this point, so many electrons will be traveling. So, with what speed they are traveling in this particular direction, with the same speed, they will be traveling in the opposite direction. So, what happens to the net current at this point? It will be 0. So, there will be no current inside a uncharged metallic conductor. So, there is no electric field applied here. I am not applied any electric field, or I am not providing any external energy to this conductor. So, this is the way these electrons which are moving inside the conductor, we call it as the free electrons. Clear? So, first point. How these electrons are made to come out of the atom? By thermodynamic internal energy. So, by thermodynamic internal energy, these electrons are knocked out of the atom. These electrons, they will be moving in a random manner. So, they collide with the positive ions. The speed of collision before and after will be the same, but after collision, they will be traveling in a random direction. So, if you take at any point, the number of electrons traveling in this direction will be equal to the number of electrons traveling in the opposite direction. So, at this point, the net effect will be 0. So, there is no current. Now, what I am going to do? I am going to connect this to a cell. So, what that means? I am giving some external energy. So, if I provide some external energy to this conductor, this external energy what you are supplying will make the free electrons to move in a definite direction. So, what will happen now? I am going to make the electron to move in a definite direction. How I made it? By supplying some external energy. That external energy what you are supplying to make the electron to move from one end of the material to the other end, we call it as the electromotive force. So, what is electromotive force? It is nothing but the external energy supplied to this conductor to make the electrons to move in a definite direction. So, simply see here we are just written taking it as electromotive force, but it is not a force. It is the work done in moving the electron from one end to the other end. How much work you are doing in moving the electrons from one end to the another end, that we call it as the electromotive force. Now here, you know what is meant by potential difference. So, at this end, the potential will be different at this end. So, these two ends will be at a different potential, that we call it as the potential. That is the work done in moving the charge to moving the charge from one end to the another end of the material, that we call it as the potential difference. Now, I will say the potential difference of a wire is, I will go for an example. The potential difference of a wire is 10 volts. What that mean? Can you see? The potential difference of a wire is 10 volts. What that means? Listen to me, cousin. I am saying that the potential difference of a wire. So just imagine this is a wire. The potential difference of this wire is 10 volts. What that means? It means that each coulomb of charge will do 10 joules of work from this end to this end of the conductor. So it means that each coulomb of charge will do 10 joules of work, or I can say 10 joule of work is done by each coulomb of charge from this end to the other end of the conductor. That we call it as the potential difference. So, what is the meaning for this? When I say if that is the potential difference, or the potential difference of a wire is 10 volts, what that mean? 10 volt potential difference means the work done on each coulomb of charge will be doing 10 joules of work from a point where the potential is high to a point where the potential is low. That is the meaning for this sentence or for this question. Now, we have seen what is meant by potential difference and what is meant by electromotive force. So, we have made the charges to flow in a definite direction. Now, the charges are flowing in a definite direction. We know that when the charges flow in a definite direction, it constitutes the current. How I can define current? Now, the charges are moving in a definite direction. This flow of charges in a unit time, that is rate of flow of charges, we call it as the current. See, the two fundamental units in current is your current in electricity as current and potential. Now, we are going to define about the current. So, how I can define current? The rate of flow of charges. That is, in 1 second, how many charges are flowing? Then we call it as the current. Unit for this is charge unit is coulomb by second. So, here mostly we will use the unit ampere. Ampere is the unit for current. Now, we can't say at all the time the charges flowing in a conductor will be the same with respect to time. It may change. So, that is the rate of flow of charges will not be the same at all the time. If that is the case, the current will not be steady, isn't it? So, most of the cases the current will not be steady. At that time, what I have to do? I have to take the instantaneous current, that I will take it as small letter I. It is given by change in charges dq by dt. So, this we call it, it's the rate of flow of charges are not uniform, then at that time I will find out this I is instantaneous current is equal to dq by dt. Just you know what is meant by current and how to define it, what is its formula and its unit, ampere. Now coming for this example, I am taking a conductor and I have connected this to a external battery, so that what happens, current will be flowing. Take a conductor, connect it to the battery. When there is no external field, no electric field, what happens? What happens to the net current inside this conductor? It will be 0. Now I connected this conductor to a battery, to a cell. Because of this, I am providing some external energy. So how will be the direction of the electric field? The electric field direction will be from the positive terminal of the cell to the negative terminal. So electric field will be flowing in this direction. The instantaneous current will also be flowing in this direction. Now let xy be the conductor. Now at this end, that is at the end y, the electron will be gaining some force. Let that force be F, because it is connected to a external cell. The electrons at this end gain some force. Let that force be EF equal to EE. So this force will make the electrons, because of the repulsion, will make the electrons to accelerate. So they will be accelerated and they will be moving in a direction opposite to the direction of the electric field. So what happens here? These electrons, what they will do, because of this external agency, external power supply, they gain some force which is equal to this much, where E is the electric field magnitude of the electron, and they will be moving very slowly with the velocity in a direction opposite to the direction of the electric field. Let that velocity, we call it as the drift velocity. Since they are drifted very slowly in a direction opposite to the direction of the electric field. How they are moving? They are moving in a direction opposite to the direction of the electric field. That velocity we call it as drift velocity. Now because of this velocity, it will gain some acceleration. So since electron is having a mass m, I want to find out what is the acceleration gained by the electrons, which is having a drift velocity vg. Then the velocity of these electrons which are moving in the opposite direction, what they will do? They will collide with each other or with the positive ions of the conductor. So when they move in this direction, they will collide with each other or with the positive ions. Because of this collision, what happens? They will be accelerated and they will be moving in this direction. So here F equal to, you can calculate this acceleration from this A equal to F by m. What is here? F, force. How much force it is gaining? It is given by E by m. So this much acceleration these electrons will be gaining. We know that. What is the velocity formula? Let tau be the time taken between two successive collisions. What is here? Tau is the time taken between two successive collisions, and Vd be the drift velocity. I can write this velocity is equal to acceleration into time taken. Here what is A here? It is given by E by m into tau. So drift velocity Vd equal to E by m into tau. Now this Vd, I can also write this as E tau by m into E. So this one remains to be the same or constant, and this quantity I will call it as the mobility of the electrons, mu E. What is here mu called? Mu is nothing but mobility of the electrons. So here mu equal to E tau by m. Clear? Now we are going to see how will be the velocity of this electron. It is going to gain some force when it is given an external electric field. When this conductor is connected to a cell, it gains some force, and this is the direction of the electric field. At this end y, the electrons will gain some force which is equal to EE, Because of this, they will be moved in this direction towards the positive terminal. When they move like this, they will collide with each other or with the ions of the conductor. Because of during each collision, what happens? They will be drifted in this direction with a constant velocity. Let that be Vt. So this Vd, because of this collision, they will gain some acceleration. That acceleration we have calculated to be E by m, where m is the mass of the electron, and just substitute this here. E by m into tau. Here E tau by m is the constant value. We are taking this as mu, where mu is called the mobility of the electron. So here I can write this mu as Vd by E. So how I can define this mobility? Mobility is defined as the drift velocity acquired per unit electric field. How I can define this? Mobility drift velocity acquired per unit electric field. Can you write the unit for this mobility? We know what is the unit for velocity? Meter per second. What is the unit for this electric field? Volt per meter. Take this to the numerator. It will become m power minus 1. It will become m square, v minus 1, s minus 1. So this will be the unit for your mobility. Now we have seen what is meant by mobility and what is meant by drift velocity. We will go for the now same thing here. The current is flowing, that is the charges are flowing in unit time. If the same charges are flowing in a unit time, in a unit area taken perpendicular to the direction of the conductor, this we call it as the current density. How I can solve this? That is number of charges flowing in unit time in unit area, that we call it as the current density. Symbol for current density is J. Here Q by T. What is this Q by T? Rate of flow of charges. This is nothing but your current. So I can also write this as I by A. So J is equal to I by A, current density. Can you write the unit for this? What is the unit for current? Ampere. What is the unit for area? Meter square. So ampere per meter square is the unit for current density. It is a vector quantity. Current density is a vector quantity. So far what we have seen? What is meant by current? How to make the charges to flow in a definite direction by applying some external energy. That external energy we call it as electromotive force. So electromotive force means it is nothing but a force. Is it a force? It is not at all a force. It is a work done in moving the charges from one end to the another end of the material. Then same here, take a conductor, same example. The electrons will be moving like this with a drift velocity Vd xy. What is current formula? Q by T. Current equal to rate of flow of charges. Now let N be the number of free electrons, or this free electrons we call it as the conduction electrons. Let there be n number of conduction electrons or free electrons in a unit volume. Here in unit volume there are n number of free electrons in a unit volume. Now I want to find out, let L be the length of this conductor and A be the area of cross section of this conductor. Now you want to find out what will be the number of conduction electrons in this conductor xy. So I have taken small letter n as the number of electrons or free electrons per unit volume. Now I want to find out the total number of free electrons in this conductor xy of length L and area of cross section A. It is given by number of free electrons or conduction electrons in the conductor xy is given by n. Here I have taken it as number of free electrons per unit volume. In each unit volume, this many number of free electrons into the volume of the conductor. So, if I multiply this number of free electrons in a unit volume into the volume of the conductor, I will get the total number of free electrons, isn't it? So, how I can write this V N A volume equal to area into length. Here we have taken the length of the conductor to be L and A be the area of cross section. So, these many number of free electrons are there in this conductor. Yeah. If E is the charge of the electron, how I can write this Q? What is Q now? Total charge of this conductor. It is given by Q equal to N E, where N is the number of free electrons in this conductor XY into the charge of each electron. That is taken as E. So, I can write this Q as N A E L. So, I know what is the total charge. Then, can I find out what is the time taken for this charges to flow through this conductor? I can write what is the velocity formula? Velocity is equal to V equal to velocity is equal to distance by length. I will take this L as the length of the conductor. Now, here I will take this velocity, that is the charges moving. L just a minute. Let L be the length of the conductor in a, let T be the time taken for the charges to move through this conductor Xy. So, velocity is equal to distance moved by time taken. Here the distance through which the charges are moving is the length of the conductor. From this, what is T? L by Vd. So, I know what is Q, I know what is T. If I know these two, can I find out what is the current? What is the formula for current? I equal to rate of flow of charges. Just substitute these two in this formula. So, I can write this current I equal to N A E L by L by Vd. This Vd goes to the numerator, LL gets cancelled. So, it will be N A E Vd, where Vd is the disk velocity. So, I found out the current flowing through this conductor to be equal to N A E Vd. So, this is the relation between the current and the drift velocity of the conductor. So, it is an important question. Now, can I bring this A to this side? So, what happens if I bring this A to this side? I by A. What is I by A? I is the current flowing in a unit area, that we call it as NEVD. What is current flowing in a unit area? This current density. So, J equal to NEVD. So, this is the relation between drift velocity and current density, and this is the relation between current and drift velocity. Now, we have seen what is the relation between current and drift velocity. Yeah. Now, you all know what is meant by Ohm's law. See, the two fundamental quantities in electricity, I have told you already, this current and potential. These two are very, very important. What is potential? What is meant by potential? Or potential difference? What is meant by potential difference? If this is a wire, this is a conductor. So, at this end, it should be having a high potential. This end is at a high potential and this end is a low potential. The charges will be flowing from this end to this end. So, there is a potential difference between these two ends. So, the work done in moving the charges from this end where the potential is high to this end where the potential is low, we call it as potential difference. So, V equal to work done on a unit per meter. Work done unit is joule, charges coulomb. This is the unit for volt, potential difference, but mostly we will use the practical unit of volt only for potential difference. We have seen for the potential V. Current. What is current? Just now we have seen what is meant by current. It is rate of flow of charges. What is the unit for charge? Coulomb. For time it is second. Coulomb per second. But what is the practical unit? It is ampere. So these two quantities are very, very important. Now, if I increase this potential difference, what happens? So this is at some potential and this is at some potential. I am going to increase the potential difference. What happens if I increase the potential difference? The charges flowing will be more. So if I increase the potential difference, that means the charges flowing are more. That means current is more. So both are directly proportional, isn't it? So if potential is more, the current is more. Both are directly proportional. This is what we are going to see in the Ohm's law. You are very familiar with the Ohm's law, isn't it? What does the Ohm's law tells you? At a steady temperature, the potential is directly proportional to the current flowing. Now I explain. So now what is meant by potential difference? What is meant by potential difference? The work done in moving a charge from one end to another end. If the potential difference is more number of charges will be flowing. More number of charges are flowing means that means more current. So if increase this will also increase this. If I put equal to, what I have to introduce? A constant. That is R here. What is R called? Resistance of the conductor. What is resistance? Resistance means it is nothing but to resist the flow of the charges. That we call it as a resistance here. Now, I will tell you a very easy method to remember this Ohm's law because this is very important. Just imagine this is O. Just divide this into 2. Again into 2. So what are the two fundamental quantities in current? In current electricity, one is I and the other is V. Both are related. So I will write this V here. Let I be here. Let R be here. Isn't it? So what does the Ohm's law tells you? Ohm's law. Ohm's law. What it tells you? Just how you can remember for your long run. O I have written. Inside this I have written all the three quantities, all the three physical quantities. One is voltage, one is current, one is the resistance. We know that V equal to IR. See here, V equal to IR. You got it. Now from this, I can write what is I? I equal to V by R. V by R. I want R. R equal to V by I. So this you should not forget. This is very, very important. Is it clear for you? Put the O, write V here because potential is very important for the flow of charges. First, I need a potential difference for the flow of charges, isn't it? So if I want to get current, first thing what I will do, I will produce a potential difference. That I have written. Because of the potential difference, I am getting current. Here, whenever there is a current, there is a resistance. See, I told you in the beginning itself a very good example, the water flowing in a river. Whenever the water flows in a river, if the bottom is smooth, the water flows without any resistance, without any stop for it, without any resistance. But if there are so many stones or dust or mud like that at the bottom of the river, what happens to the flow of water? It won't be flowing at the same speed how it flows in the initial. First example I told, the bottom is smooth. There is no resistance to stop the flow of water. There is no stop, isn't it? Nothing is there to resist the flow of water. But here in this example, there are so many stones or pebbles or mud or stick, whatever it may be. These things, they will stop the flow of water. Now that we call it as the resistance here. So Ohm's law gives you the relation between the voltage and the current. Now here in this example, we have taken the drift velocity Vd is equal to, or current we have taken I equal to NAEVD, isn't it? What is here drift velocity? Ed equal to E by M into tau. Already we have seen what is the drift velocity. It is given by E by M into tau. Substitute this Vd there. What happens if I substitute this value here for the current relation? Just now we have seen NAE E by M into tau. It will become NA E square E by M into tau. Isn't it? I. What is your E? Electric field intensity. Let L be the length of the conductor and V be the potential. How I can write this? E equal to, E is given as V by L, potential gradient. So, E equal to V. In the place of E, can I substitute this? It will become NA E square V by Lm into tau. I equal to this much. Now, here I can also write this as NA E square tau by Lm into V. I equal to, this is the relation. Now, in this relation, this N A area of cross section, N is the number of free electrons in this conductor, and E is the charge of the electron, L is the length of the conductor, and M is the mass of the electron, and tau is the time taken for during successive collisions. All these are constant. We can write this as, we know that I equal to V by R. I can write this equation in this form and I can verify the Ohm's law now. So, I can write I equal to V by R. What is R here? That is N A E square tau by L M. This is by R. If I want to write R, it is nothing but L M by N A E square tau. So, this much of resistance is suffered by the conductor when a current I flows through this. So, R equal to ML, where R is called the resistance of the conductor. So, we have proved the Ohm's law. Here V and I are directly proportional. Now, I prove the Ohm's law in this equation. Ohm's law only for a constant temperature. When the temperature does not change, I can say the potential is directly proportional to the current. So, I equal to VR So, if I draw a graph between the potential and the I, potential in the x-axis and I in the y-axis, I will be getting a straight line graph for ohmic conductors. That means both are directly proportional. If I increase the potential, simultaneously the current will also increase. In those, the reciprocal of resistance, we call it as the conductance. What is conductance? The reciprocal of resistance. What is the unit for resistance? Unit for resistance is ohm. For conductance, it is mho or ohm per meter minus 1. Now, we will see on what factors this resistance will depend upon. The resistance of a conductor will depend upon the material of the conductor and also on the dimension of the conductor. And what factors does the resistance of the material depends upon? Depends upon the material of the conductor and it also depends upon the dimension of the conductor. Now, I will take we'll go for two examples for finding out the factors on which the resistance depends upon. I will take a slab. We'll take another slab. So, both are identical slabs. Here what I am doing here, I am taking a two slabs which are identical to each other. Let the potential develop in first slab be V. So, let L be the length of this conductor and A be the area of cross section. So, it's same size, same length and area of cross section, same identical slab I am going to attach to this. I am just going to keep it next to it. Because of this, let V be the potential developed in the first slab. Here, it will also produces its potential. So, there will be some potential difference in this slab. Let that be V. How much current is flowing in this conductor? The same current will be flowing in this conductor. Let I be the current flowing in the both the conductors. Now, for the here, we know that V equal to IR. From this R equal to V by I. This is the resistance suffered by this first slab. Now, I want to find out what will be the resistance suffered by this slab also. when the length is doubled. Here the initial length, the length of this conductor is L. Now it has become 2L. I have doubled the length of the conductor. Now we are going to see, if I double the length of the conductor, what happens to its resistance? The initial resistance is R equal to V by A. Now I double. So what is the total potential developed here? The potential developed for each conductor is V. So V plus V, it will be 2V. So let 2V be the potential developed, and I will be the current flowing in both the snaps. How much current is flowing here? The same current will be flowing here. Now the new resistance, when the length is doubled, it will be R equal to 2V by I, isn't it? So what I did, I doubled the length. Length double பண்ணிருக்கும். This V by I is R. So it will become twice the initial resistance, isn't it? So what happens to the new resistance here? When the length is doubled, it has become twice the initial resistance. That is, the resistance increases when the length is doubled. Now what I am going to do here, I am going to take a slab of length L and area of cross section A. I am going to cut this into two equal halves. What I am going to do, I am going to cut this into two equal halves such that this area of cross section is A by 2 and this area of cross section is A by 2. So a single slab of length L and area of cross section A, let I be the current flowing in this conductor. I cut it into two. That is what I am doing. I am decreasing the area. That is half of the area of cross section. What happens to this? The total current flowing in this slab is I. So here it will be I by 2. Here it will be I by 2. Initially for this conductor, how will be the resistance? R equal to V by I. We want to find out what is the final resistance when this slab is cut into two equal halves. It's identical slab. It will be equal to, what happens to the potential here? It will be the same. What happens to the current? It is I by 2. So V by I by 2. 2 goes to the numerator. It will be 2V by I. So what happens to the new resistance now? R dash, it is equal to 2V, this V by I is nothing but your initial resistance. So when I decrease the area, what happens to the resistance? It increases. So when I double the length, its resistance increases. When I decrease the area, its resistance increases. So from these two examples, what conclusion you can get? What conclusion we got now? This resistance is directly proportional to the length in the first example. I double the length, isn't it? So what happened to the resistance? It increased. So if I double the length or if I increase the length, its resistance increases. The second example, I decrease the area. What happens to the resistance? It increases. So here the resistance is inversely proportional to the area of cross section. That is the conclusion we are getting from these two examples. So R equal to, R is inversely proportional to A. So I can say this resistance is directly proportional to the length of the conductor, is inversely proportional to the area of cross section of the conductor. So R is directly proportional to L by A. Together I am writing like this, R is equal to. So if I put R equal to, it will be, I have to introduce the constant. Let that be specific resistance or electrical resistivity, rho L by A. So here rho is a constant, that we call it as the specific resistance or electrical resistivity. How I can define this? If this L is equal, length of the conductor is 1 meter and area of cross section is 1 meter square, what happens to the resistance? Specific resistance. So the specific resistance is numerically equal to the resistance of the conductor when a conductor of unit length and if its area of cross section is 1 square meter. In this way I can define the specific resistance or electrical resistivity of a conductor. The unit for specific resistance is ohm meter. The the reciprocal of specific resistance, we call it as the conductivity or electrical conductivity sigma. The unit for this is mho per meter. You can also write this as like this. So we have seen what is meant by resistance and what factors it will depend upon. It is directly proportional to the length and inversely proportional to the area, R equal to rho L by A, where rho is called the specific resistance or electrical resistivity. Its unit is ohm meter. The reciprocal of resistance is electrical conductivity and its unit is mho per meter. Now, we know what is the conductor. So, based on this electrical resistivity, I can also classify the material broadly into three main categories. So, what I am going to do, based on the resistivity, we are going to classify the materials as conductors, as insulators and also as semiconductors. Based on this resistivity value of the material, I am going to classify the materials as conductors and as insulators Now, if it is a conductor, what that means? It will allow the charges to flow through, isn't it? What happens then to the resistivity then? It will be low or high, can you say? If it is a conductor, the term itself indicates to allow the charges. It's conducting. That means its resistivity will be low. So, it will be having low resistivity, first point. I have to specifically mention the range or the value of this resistivity for a conductor. It will be of order of 10 power minus 6. Just imagine 10 power minus 6, that is 0.06 times 0.01. 10 power minus 6 ohm meter to 10 power minus 8 ohm meter. This will be the range of the resistivity for a conductor. It will offer very low resistivity for the flow of charges. What happens if the temperature increases? Resistance also increases for a conductor. Then go for the insulator. We know that the word itself indicates. We know what is the meaning for the insulator. It will not allow the flow of charges. It will not allow the charges to flow through it. That means it will be having high resistivity. It will offer very high resistance for the flow of charges. Then what happens to its value? It will be 10 power 8 to 10 power 14 ohm meter. This will be the value of the resistivity for insulators. For insulators, if the temperature increases, this resistance decreases. Now, in between these two, we will be having another material called semiconductor. That is, it is a partial conductor. It will allow a few charges to flow through. That we call it as the semiconductor. In semiconductors, the resistivity value will be 10 power minus 2 ohm meter to 10 power 4 ohm meter. So, this will be the resistivity value for semiconductors. Now, we have seen examples, so many examples we can say for conductors. The very good examples for semiconductors are germanium and silicon. Insulators, so many examples I can wood, Teflon, plastic, all these are good examples for insulators. For conductors, all metals are very good examples for conductors. Now, we know that in a conductor, if I increase the temperature, what happens to the resistance? It also increases, isn't it? Now, we will draw a graph between the temperature and the resistance for a conductor. I am going to decrease the temperature. If I decrease the temperature, its resistance decreases. For a few materials, for some material, if I decrease the at a particular temperature, suddenly its resistance falls to 0. What will be happening for certain materials? Its temperature, at a certain temperature, its resistance value will become 0. That temperature we call it as the transition temperature. So, what is meant by transition temperature? At a temperature, at a particular temperature, the resistance of the conductor becomes 0. That means its conductivity value will be very high. What happens to its conductivity? It will be very high. So, now at this temperature, that is the transition temperature, the materials are called superconductors. Now, why these are called superconductors? With zero resistance, they are offering the conductance. That is why they are called superconductors. So, at some certain temperature, the materials which are very good conductors become superconductors only at this transition temperature. Very good example is mercury. So, transition temperature for mercury is 4.2 Kelvin. That is, at a temperature of 4.2 Kelvin, there will be no resistance offered for the conductivity of the mercury. That is the meaning for this. So, what we have seen now in this chapter, current, electricity. Now, we have seen what is going to be potential difference. What is going to be potential difference? The work done in moving the charges from one end to the other end of the conductor, that we call it as the potential difference. What is the, see, I have a battery now. I am saying this battery is of 9 volts. What is the meaning for it? I am saying that if this is a battery of 9 volts, what that means? This is a battery of 9 volts. That means each charge or 1 coulomb of charge coming out of the cell or the battery, coming out of this battery will do 9 joules of work before re-entering the other side of the battery. So, that is why it is having 9 volt as the potential difference. Can you understand? We know what is maybe potential difference. What is maybe potential difference? Work done in moving a unit positive charge. Clear? Now, I told this battery is a 9 volt battery. That means each coulomb of charge or a charge of 1 coulomb will do 9 joule of work when it comes out of the one end of the battery, one side of the battery. It will do how much work it will do? It will do 9 joules of work before re-entering the other side of the battery. That is the meaning for this. Clear? If I say a battery of 1.5 volts, I am just telling there is a battery of 1.5 volts. What that means? A coulomb of charge, or each coulomb of charge, when it comes out of one side of the battery, it will do 1.5 joules of work before re-entering the other side of the battery. So, thus that is the meaning for this. Clear? So, in this current electricity, we have seen what is meant by electric current and what is meant by drift velocity, current density, and the relation between current and drift velocity. And we have seen what is the familiar law, Ohm's law, what is meant by resistance, and what is meant by electrical resistivity, electrical conductivity, and how to classify the materials as conductors, semiconductors, and insulators based on the resistivity value, that and all we have seen.